So think about this. We've gone from building a simple house, our classic monolith. Then we learned how to build a massive skyscraper, our microservices. But what happens when even a skyscraper isn't big enough? Well, today we're taking the next leap. We're not just architecting a single building anymore. We're architecting an entire digital city. And when you're building a city, you get city-sized problems. I mean, look at this question. This isn't just a coding challenge anymore, is it? This is about physics, it's about time, it's about getting thousands of computers to agree on a single truth. This is the deep end, folks, and these are exactly the kinds of problems we're going to solve today.
So here's our blueprint. First, we need to establish the law and order of our city. That's all about truth and agreement. Then we'll build the commercial engine to handle massive scale transactions. After that, we'll look at the city's archives and its construction cranes, how we handle data history and deployments. And finally, we'll wire up the city's nervous system and make sure everyone's speaking the same language.
All right, let's get our hands dirty and lay the foundation. First things first, how do we establish a single source of truth that everyone agrees on? And how do we plan our city grid so it can grow to a massive size without just crumbling?
In one simple database, truth is easy. It is what it is. But what happens when you've got 500 servers, maybe scattered all over the world? Server A in Virginia says your bank balance is $100. Server B in Frankfurt says it's 90. And server C in Tokyo is completely offline. Who's right? How do they possibly agree? This, right here, is the consensus problem.
To really get why this is so tough, there's this classic thought experiment. You've got two generals on two different hills, and they need to coordinate an attack. General A sends a messenger, attack at dawn. But did the messenger make it? He has to wait for confirmation. Okay, so General B sends a confirmation back. But now, can General B be sure that messenger made it? You see the problem? No matter how many messages you send back and forth, you can never, ever be 100% certain the other side knows the final plan. Over an unreliable network, and all networks are unreliable, perfect certainty is literally impossible.
So if perfect certainty is impossible, how does anything in the modern internet even work? Well, we cheat. We settle for good enough certainty. And we do that with brilliant algorithms like Raft. Here's the gist. The servers elect a leader. When a change comes in, the leader tells all its followers, hey, this is the new truth. It doesn't wait for all of them, though. It just waits for a majority of them to write it down and say, got it. Once that majority agrees, that's it. It's the new law of the land, and the system moves on. This is what powers so many of the systems you use every day, like Kubernetes.
Okay, so we can agree on things. But what about growth? How do we split our 10 million users across, say, 3 servers? The simple, naive way is to just use a modulo operator. But here's the catch. The second you add a 4th server to handle more traffic, the math changes for every single user. You have to reshuffle everything. It is absolute chaos. The much, much smarter way is something called consistent hashing. Just imagine a clock face. You place your servers on the clock at, say, 12, 4, and 8. Then you place all your data on the clock, too. And the rule is simple. Data just belongs to the first server it finds moving clockwise. Now, if you add a new server at 2 o'clock, what happens? You only have to move the data between 12 and 2. It's a beautifully elegant solution that lets you scale with minimal disruption. All right, our city grid is planned, and it can grow. Now it's time to build its engine of commerce. How do we handle really complex financial transactions? Like when you place an order online, and it has to talk to the payment system, the inventory system, and the shipping system all at once.
When you can't use a simple, old-school database transaction, you need something called a saga. And really, it's like a choreographed dance between services. The order service kicks things off. New pending order. It sends out an event. The payment service hears that and goes, my turn. It charges the credit card and sends out its own event. Then the inventory service hears that, reserves the stock, and sends out its event. Finally, the order service hears that everything went well and sets the order to confirmed. See? A perfect chain reaction.
But what if the dance goes wrong? What if the inventory service realizes, uh-oh, we're actually out of stock? It can't just stop, it has to announce the failure. It publishes a stock failed event. And this triggers a series of compensating transactions, which is basically a fancy way of saying everybody dance backwards. The payment service hears the failure event and immediately refunds the credit card. The order service hears it and cancels the order. The whole system cleans up after itself. And this really gets to the core of sagas. You have to be just as thoughtful about coding the undo steps as you are about coding the do steps. Now, our city's commerce needs to be fast, so we use caching. But caching has this one terrifying dark side. Picture this. You've got a super popular piece of data cached, like the front page of a news site. Its cache expires. In the very next millisecond, 5,000 people all try to load the page. What happens? All 5,000 of those requests miss the cache and slam your poor database at the exact same instant. The database just collapses. That is the thundering herd, and it can bring your entire system down. Luckily, the solution is surprisingly simple. It's called request coalescing. Here's how it works. The very first request that misses the cache gets to set a tiny little lock. It's basically putting its hand up and saying, I got this, everyone chill for a second. It then goes off to the database to do the hard work. Any of the other 4,999 requests that show up see the lock and just wait. They just pause for a few milliseconds. By the time they check again, that first request has already gotten the data, put it back in the cache, and unlocked it. Problem solved. Okay, our city is growing. The economy is humming along. Now let's talk about the city's memory, its archives, and its ability to evolve. How do we keep a perfect record of everything that's ever happened? And how do we upgrade critical infrastructure, bring in the construction cranes, without shutting down the whole city? Most systems just store whatever the current state of the world is. Your balance is $50. You spend $10, so we just delete the 50 and write a 40. The fact that you deposited money last week? Gone. The history is lost. But with event sourcing, we change our mindset. We never delete or overwrite anything. We just keep an immutable log of everything that's ever happened. User created, deposited $50, purchased $10. If you want to know the current balance, you just replay the events. It gives you a perfect, flawless, auditable history of your entire system. It's the city's official archive. So how do we upgrade our city without causing chaos? Well, one popular way is called a canary deployment. It's named after the old canary in the coal mine trick. You roll out your brand new version of the software to just a tiny slice of your users, maybe 5%. And then you just watch. You stare at your dashboards like a hawk. Are error rates going up? Is latency spiking? If anything looks even slightly wrong, you roll it back instantly. But if it all looks good, you slowly, carefully open the floodgates to more and more users until everyone is on the new version. Another great strategy is called blue-green. This one's a bit different. You actually build out an entire second identical copy of your whole production environment. We'll call it green. Your users are all still on the old blue environment. Once you're 100% confident that green is working perfectly, you just flip a switch at the load balancer. And bam, instantly all traffic is redirected to the new green environment. The best part? If you find a problem, you just flip the switch right back. It's an incredibly low-risk, all-or-nothing approach to deployments. So our city is now vast, it's complex, it's constantly changing. For our final piece of the puzzle, we have to tackle two of the hardest questions. One, how do we actually see what's happening everywhere at once? And two, how do we make sure that all the different people building our city are actually speaking the same language? To really understand a complex system, just looking at log files isn't enough. You need something called observability, and it rests on three pillars. You've got logs, which tell you about specific, discrete events. You've got metrics, which give you numbers over time, like CPU usage. But the real magic, the absolute game changer, is tracing. A trace can follow a single user's request as it jumps through 10 different microservices in your system, and it'll tell you exactly how long it spent in each one. It's the nervous system of your digital city, letting you pinpoint exactly where the pain is. Now for our last concept. And it might sound philosophical, but it is maybe the most important one of all. I want you to just take a second and ask yourself this question about your own company. What does the word user actually mean? Seriously, because I guarantee you that one simple word can mean dangerously different things to different teams. Think about it. To your sales team, a user is a lead with a phone number to call. To your shipping team, a user is a recipient with a physical address. To your login team, a user is an account with a hashed password. Domain-driven design tells us to stop trying to force one giant monstrous user object to work for everyone. It's impossible. Instead, we create what are called bounded contexts. Inside the sales context, they have their own lead model. Shipping has its recipient model. They are separate, they are clean. And this is the secret to letting hundreds or even thousands of developers work on a massive system without constantly tripping over each other. And really, if there is one single idea that ties everything we've talked about today together, it's this one. Our job as architects, at the end of the day, isn't to create complexity. It's to find elegant ways to manage the complexity that is already there. So what is the final blueprint? It's the understanding that all of these fancy advanced patterns we've discussed, sagas, consistent hashing, event sourcing, they're not things you use just to sound smart. They are heavy-duty tools that you bring out to fight complexity when it becomes absolutely unavoidable. The best architects are the ones who know when to keep it simple. And now it's your turn to build. I'll leave you with a final thought experiment. Think about a system like Instagram. How do you think they handle the ultimate thundering herd problem? When a celebrity with 200 million followers posts a new photo, and all of their phones try to fetch it at the exact same time. The patterns are there, the blueprint is in your hands now. Go build something amazing.